Okay, so we'll continue what we did last time, which is this one here. And I'm lucky that I was able to just find the question again, because I think Grok basically overrode the name of the conversation where I had the idea. I think I'm going to just put it, I think I'm just going to put it next time somewhere else in here. So now the question, just give me a second, guys. Cool. So, but at least I can see that that Grok got it wrong, right? So he said, so Grok thought for 13 minutes, and his answer was 1, and we know the answer is 5, the correct answer. So that's now time for us to kind of dive into this and try to understand what's going on, and learn some useless but interesting stuff. So. First things first, I think one of the things that I need to do first is understand really what they are even asking, right? Because most of these math questions, those are kind of proofs, right? So the way that you approach these most of the time is by, you know, sort of understanding and specifying the starting point, trying this, then sort of formalizing what it is that they're trying to ask, what they're trying to prove, and then basically find the way from A to B, right? Find the way from the starting point to the end point. But that's the first thing, is I'm just reading these, like let S equal like this, even I don't even know what that means. So, and I think that in and of itself is going to be an interesting thing. So let's just ask Grok, and maybe that's just the problem, right? So the way that I've copied it, pasted in here, because maybe it just does not really understand because I don't know if this is the right way to, like, the right notation for this stuff. Help me understand what this means. So I'm gonna take a screenshot because I think that works better. Let's try to work out what went wrong, because that's the wrong answer to the solution. I first wanna break down the exercise, or basically the question. Can you start by explaining me what does the attached image mean? That's the advantage of using these tools, right? I want a quick answer. We don't need it to think all the time in expert mode. Okay, so let's see. This question is this one here. So I'm gonna copy, because that's the LaTeX. So it says the attachment is supposed to be a garbled corrupted version of mathematical expression. It seems to a set or group S with an equation. Okay. I think that might be where it just gets it wrong. I think the LaTeX expression reads like this. I'm assuming this is a group rather than a set, given the nature of the problem. wrong. Okay, so now we got something, extra special groups. Quick answer. Is indeed unusual. Like a misreading? What? Okay, none of these. Then I'm really gonna ask. I'm really gonna ask. Okay, no, maybe. The notation doesn't directly correspond to standard group definition, but we can hypothesize based on the problem structure. The exponent 1 plus 2 equals. I mean, this makes no sense. A group of order 3 raised to some power or a specific construction, but it's not standard. Why wouldn't it be standard? Like, why wouldn't someone just put this? This is okay. None of these cancel. So let me just ask again. In expert mode, I think it was at least giving me a better answer. So that is something that I like more. So can I open that more? So it's the extra special group of order 27. Like the Heisenberg group modulo 3. There's a lot to unpack in here. So the last expression, this like comes from group theories, extra special groups. Let's dive into extra special groups. What are extra special groups? Again, remember we're kind of like digging a knot. The way that I like to do these is these. So if I think of a, that's the surface of the problem, and we're essentially like, we kind of like dig a knot in here to understand what's going on, to understand what's, we're gonna keep doing things like these, right? That's gonna take we have to be patient. That's the problem here. Those are complicated questions because we don't know a lot of the elements in there. So extra special groups. So what are extra special? What are extra special groups in group theory? So while it's doing these block theories, so comes from a group theory. 4 is the extra special group of order 27. S has normal subgroups, isomorphic 2, okay, with quotient. Okay, so this might be things that might come in handy for the proof, maybe, I don't know, because it does actually, this actually appears in the, yes, that appears here as well, as divided by, I mean, it's not a division, but like as over. I don't know how you would call it, how you would name these, but okay. In group theory, extra special groups, also called extra special or extra special P group, is a specific type of a non-abelian P group, a group whose order is a power of a prime P that satisfies the following equivalent conditions. So that's exactly, so that's good. That's what we look. So these are the characteristics of extra special groups. Now, let's unpack these. I've seen these, but I'm not too familiar with these. So, it would be interesting to have a way to basically sort of explore this. I know Perplexity does this, where you can just expand on specific elements of an answer. What It's a non-abelian group. Okay. So now it's commutative, so we know these. Where AB, is a group where the binary operation is not commutative for at least some elements. So exist elements A and B in G such that A times B is not the same as B times A. I mean, I say times because that's just like a generic operation. So it's non-commutative. Ordering structure can be finite or infinite. And relevance is fundamental in abstract algebra, representation theory, and applications like physics, symmetry groups, and quantum mechanics. Cryptography, non-commutative adds complexity. Yes. Examples: S3. I know S3 because that popped up in some of the quantum stuff that I did a few years ago. Just to be clear, this is way above my pay grade in terms of my core math knowledge, right? So we're really exploring here, and I'm really not reading all of these on purpose. I'm just like cherry picking the things that I want to dig into. So we've got the non-abelian groups are the ones with non-commutative operations, and then it also mentioned something about P groups, right? So special groups. So extra special groups is a specific type of non-abelian P group. A P group is a group whose order is a power of a prime. What's the order of a group? Is the number of elements. Okay, I suspected it was something like these. Could be finite, infinite. So G is a positive integer. The symmetric group S3 has order 6, as it contains 6 permutations. The order of a group is the number of elements in G. Can you give me a more detailed example of a group and its order calculation? Yeah, that's a classic example. Okay, so of a finite non-abelian group because of all. So the group operation is composition of permutations, applying one permutation after another, which is associative but not commutative in general. So the empty cycle. Then transposition swaps 2 elements. Swaps 1 and 2 leaves 3 fixed. Swaps 1 and 3 leaves 2 fixed. To find the order, we list all the distinct permutations. Then 3 cycles. Okay. So it's 5, I guess, the order, and then plus probably the identity, which means that it's probably 6. Yes. Klein 4 group, V4, and abelian group. The Klein 4 group denoted Z. So this is just notation, right? Where this notation comes from, this is crazy. The symmetries of a rectangle that aren't rotations. Or equivalently, the dark product of 2 cyclic groups of order 2. Think of it as a set EABC with the operation where every non-identity element squared is identity and products like A times B equals C, etc. explicitly. So these are the symmetries of a rectangle that are in rotation. So you have flip horizontal, flip vertical. Yeah, but there are in rotations, right? So why are you including a rotation? Yeah, okay, so you're okay, cool. So essentially you have, I mean, this is really the definition of a group, right? Which means elements and operations. For some reason, they like to talk about symmetries a lot. I think that's just one way to see groups. But okay, we were back at so let's go back at here at the what this expression means. This is a group, right? So we're trying to understand, we're trying to define S as a group. Now, what does this group represent? It's a group. Here says comes from group theory, so it's the extra special group of order 27. Help me break down this expression. I mean, let's go back to the definition. Help me break down the notation here, please. Why are we seeing the 1 plus 2 exponent? And yeah, that's one question. And then what is 3? I'm assuming that's just the name of a specific group, right? Finite P group, particularly an extra special P group of okay, extra special P group for the prime P equals 3. Okay, so it's a group. Okay, so what are P groups? So it's going to be something about like primes and operations over primes, maybe? So it's going to be something about primes and operations over primes, I think. A P group, also called a prime power group, is a group G whose order is the number of elements in G. Wait. A prime power group is a group G whose order, the number of elements in G, is a power of a single prime number. Okay. So the order, okay. That's for some non-negative integer k. So P groups are groups. It's a special type of groups that basically, yeah, it's defined by the characteristics of the order. I'm thinking this is, it's like saying what are prime numbers, right? So there are numbers who satisfy a certain condition. In this case, so maybe those are like the prime numbers of the group theory kind of thing, right? So it's basically groups whose order is a power of a single prime number. Why are these groups important? Relevant? Keep it short. It's just out of curiosity. Add a bit of context. Okay, they form building blocks for other finite groups like via Sylow theorems, and helping classify, decompose larger groups. Okay, yeah. Nilpotent with non-trivial centers, simplifying their structure for study. They're okay, so they're just basically simpler to look at and to study. They arise in representation theory, modular reps, topology, number theory, and the classification of finite numbers and groups. Okay. So basically, they pop up in other areas and so on. I mean, this is like a rabbit hole, really. But okay, so it's telling me that things that basically the base, so let's break down notation. The base 3, this indicates that the group is a 3 group, meaning it's okay, so it's not a specific group. It's just trying to say, okay, we're gonna come out with a group S, and they're just telling us it's a 3 group. It's a P group, right? But with P equals 3. So this is, if I ignore the exponents at the point, like right now, it's just telling me that it's a group whose order is a power of 3. Yeah, of the prime 3. Specifically, all elements have orders that are powers of 3, and the group is finite. Power of the prime 3. The exponent 1 plus 2 is not a simple arithmetic exponent like in basic algebra, not literally 3. Instead, it's a conventional shorthand in p-group classification to describe the group's order and structure. So the order of the group S is 3 to the power of 1 plus 2, 3 to the power 3. Right. Reflects the internal structure of extra special groups. The center, ZS, the subgroup of elements that commute with everything, has order 3 to the power of 1, 3, and the quotient S divided by ZS is an elementary abelian 3 group of order 9, which is isomorphic to C3 and C3. I don't know how, I'm gonna, this is very naive, right? But I'm just saying C3 times C3, where C3 is a cyclic group of order 3. In general, for extra special P groups, the exponent is written as 1 plus 2m, where m is a positive integer, emphasizing the minimal non-abelian nature. A central extension that's just one step beyond abelian. Whoa. I need to unpack this. There's okay, that's definitely, I think I should focus on that. Let me just look at the subscript though. It distinguishes between the two isomorphism classes of extra special 3 groups of order 27. First, why are we doing 1 plus 2? Why do we do these? So why is it notated like these? 3 to the power 3 is 27. So it doesn't get the group is a 3 group, meaning, okay. Because if we go back to this for a second, so we're defining a group here. We're defining a group S, we're defining a group D, and then we're defining another group G that is a, whatever that is. I don't know what that operator is. And we don't know what action of S is on D. But then there's a relation to the only possible non-trivial action in D. And so it's asking what let the K be a large enough field with characteristic 2. How many blocks does KG have? So it's asking us about G, right? So we're defining the first part of the first part of the question here is defining S, D, and G. And the question is actually about a property of G. And so maybe I'll ask what are blocks. I'm just kind of jumping a bit like from this section to this section just so that I clear my head a little bit, because this is very dense. This is very dense, but okay, so we're talking, I mean, we're it's notation for sure. It's telling us the order, right? Maybe I shouldn't really care about why, but maybe yes, because there's a reason for this. There's a reason for these notation, right? Next one is written as 1 plus 2m, emphasizing the minimal non-abelian nature. A central extension that's just one step beyond abelian. So why does can you expand a bit more the rationale behind the notation? Because essentially what yeah. Okay, so now we've got a general thing. So P, so that's a general notation. For extra special P groups encapsulates their structural properties in a compact way, drawing from the definition as non-abelian P groups where the center, what is the center? In the even dimensionality required by the group's non-abelian nature. The one directly reflects the minimal center. And 2M enforces that the dimensions of the vector space is even. Again, this might just be too deep, right? I don't know, at some point I have to kind of cut and stop digging in a certain definition, but it's but okay, we've dissected that. At least this tells us a bit about the structure. I don't know what is the center. What is the group center? When you say the center, what do you mean? Can you expand more on what the center of a group is? I mean, the speed in which you can break down a problem is insane, right? Because, like, if you look at some of the videos that I used to do in the past, maybe similar in nature, like I would have had to search like an insane amount of like Wikipedia articles and things like these. So let's go. So in group theory, the center of a group, from Zentrum, meaning center, is a subset of elements in G that commute with every other element in the group. Okay. In other words, it's the central part of the group where the operation behaves commutatively with respect to the entire group. Let G be a group of with an operation, often written multiplicatively, but it could be in addition for additive groups. The center is defined as all the Z elements G, such that Z times G equals G times Z for all G of G. Okay. Why is it called center though? Okay. Because the elements are central to the group. They commute with every other element, meaning multiplication, or the group operation from left to right yields the same as result, in a sense of symmetry or centrality. Okay, yeah. I mean, it's probably useless for the question, but it's fine. Let's go back to the notation. So essentially, the extra special P groups encapsulate the structure properties in a compact way. So the definition of non-abelian P groups where the center. So we know non-abelian means that not everything is commutative, but you can still have a center, right? So you can still have a bunch of elements in that group that do have commutativity, and this would be the center. And so the center is ZG of that group, of the commutative subgroup, and the Frattini subgroup, whatever the fuck this is, all coincide and have order P. Okay, so 1 second, drawing compact way. Drawing from the definition as non-abelian P groups where the center, commutator, the commutator subgroup. Okay, so these are three. So what is the commutator subgroup? I'll have to stop now. I'll probably do another video today. But yeah, we're there. We're there. I should pin this one. Can I pin it? No, I'll just leave it here. All right. So we keep those conversations. What is a derived group? Group G is the subgroup generated by all commutator elements in G. A commutator of two elements is defined as. No, okay, that's another can of worms. we'll get into that in the next session. See you guys.